The basics of area video for circles kind of already talked about how we understand the formula for area of a circle and area of a sector. So this isn't going to rederive that. If you're curious, go look at that video. We're just going to use these formulas here and kind of breeze through this note page and do some practice. So area of a circle was either pi r squared or in terms of diameter, pi d squared over 4. To find an area of a shaded region like this, we saw in the last section, we can subtract. So we can do pi times 6 squared minus pi times 4 squared. So that's 36 pi minus 16 pi. We would get 20 pi square inches. Should be pretty basic stuff there. Area of a sector, also I talked about in that video, so you can go back and look at that, but it's the same idea as a proportion of the area, as an arc length is a proportion of a circumference, or as the angle measure of the central angle is out of 360. So we have the area out of the total area, just like we had arc length was the length of AB over 2 pi r. Same exact relationship. So we can use this equation or not memorize a formula and actually just think about how it works. So area of sector XOY. So it's not the triangle XOY, it's the sector, so it includes all of this. We have 120 degrees for this arc. Remember, that means our central angle is 120 degrees. That's out of the total 360, which is 1/3 of the circle. So since we have 1/3 of the circle, we have 1/3 of the area. So the area would be 1/3 times pi times our radius, which is 3 squared, which I'm actually going to write that as times 3 times 3. That way I can cancel out this 1/3 and this 3, and our area is just 3 pi. And we do have units, so 3 pi square centimeters. All right, so areas of segments, we can, remember, get the measure of our central angle several different ways. We can get it from the arc measure or the central angle or whatever. So it's saying here the area of a segment of a circle. So the segment is this part. So same word we use for line segments, but this is a segment of a circle. And they're saying we can take the area of a sector minus the area of that triangle and treat it basically like a shaded region problem. So we find the area of this entire thing here, and then take away this part, and we're left with just this segment, this little outer crust part. So let's find the area of the minor segment bounded by segment XY and arc XY. So that means this part in here. First of all, we need the area of the sector. So we'll call the sector area sector. And then we're going to find the area of the triangle, and we're going to subtract them. Total area is going to be sector minus triangle. So our sector, we have 60 degrees out of the total 360. That's 1/6 of our area. And then we have pi times 4 squared. So pi times 16. 16 over 6 simplifies to be 8 over 3. So that's as simple as that gets, is 8/3 pi. And that's in square inches, and then that's this part here. Now we need the area of the triangle. So the area of the triangle, we know that it's an isosceles triangle, and we know that this is going to be a 30, 60, 90 triangle. Because the central angle was 60, we're bisecting it with a radius. Remember, if we draw a radius through a chord, then it's always going to be a perpendicular bisector of that chord. So that radius gives us a 30, 60, 90 triangle. I'm going to redraw that triangle here, so I'm going to draw it kind of in the same orientation. So we have our right angle. We have S, 2S, and S root 3, since it's a 30, 60, 90 with the 30 over here. Now, I know 4 inches is 2s. So 2s is 4. So s is 2. And then the height of the triangle would be 2 root 3. So in total, if I'm looking at this triangle, it actually has 2 of these. So I have s here again. So this is, of course, an equilateral triangle, since it was 60, 60, 60 to begin with. So we have a base, we got 1/2. The base is 2 plus 2, so that's 4. And the altitude, the height, is 2 root 3. I'm just going to cancel out that half and that 2. So we get 4 root 3, and that would be in square inches. So that's our second area. So our total area in a precise answer would be 8/3 pi minus 4 root 3, and that would be in square inches. Now I do want to go to Desmos and compare, like, to get the actual, like, answer of what that means. So let me pull Desmos back over here. All right. So we're going to do 8/3 times pi minus 4 times the square root of 3. So that is about 1.4, about 1.5 inches that we're ending up with. So that's about 1.45 square inches. Yeah, so that's, I want us to be able to do both. I'll probably be asking you to find both the precise or exact area and a rounded estimate. So I want us to be familiar with doing both of those. All right, so that's pretty much all for notes on that. I'll do a few more practice problems, and then you can do the rest on your own. All right, so we're going to find the exact area of these circles and then a rounded area. Perfect. So exact area is going to be pi times 3/8 the radius squared. So our exact answer would be the square of this, 9/64 pi, and it's going to be in square inches. Now I know that doesn't simplify because 3/8 doesn't simplify, so when I square it, it can't simplify either because this is made of 3's and this is made of 2's. All right, so if we wanted to find an approximation for that, or a decimal version to the nearest hundredth, that would be 9/64, not 9 minus, 9/64 times pi. So that would be 0.44 square inches. All right, second one, we have 3.7 centimeters. So I'm going to put, this is number 2. So we have pi times 3.7 squared. I have no idea what that would be. So that's a 9, that's a 4, that's a 21, 25, and that's a 0, that's a 1, that's a 2, that's an 11. Get 2 decimals because we had 2 decimals there. So that would be 13.69 pi. And then if we approximate that using Desmos, we'll get 13.69 pi is right at 43. I'm going to make sure I did that square right. 3.7 squared. Yes, good. Okay, so 43.00. So this is in square centimeters. And we would say is approximately, I already forgot the number, 43. And we still put approximately because it's not exactly 43, right? There's still more decimals that we didn't go to beyond the hundredths place. So we use this kind of wavy equal sign for an approximation. Number 3, we have 5 3/4. That's not great. So we have pi times, we're going to change this to all quarters. So 5 in fourths is 20. So we'll make that 23 fourths, which of course doesn't simplify, and we're going to square that. So as a precise answer, we have 23 squared. I don't know what that is either. So that's 9, 6, 0, 6, 4, 529 over 16 pi. And our units are square inches. And again, we know this doesn't simplify because this doesn't simplify, right? The 23 is still all the factors of this, and the 2's that were factors here are all the factors of this. So there's no way that this bigger version can simplify when it's still made of the same factors as this one. So our approximate answer here, let's get the calculator. So we have 529 over 16 times pi, 103.87. 103.87 square inches. All right, so that's the kind of thing we're doing with areas of circles. This is just solving backwards, so using the formula and solving for R or D. So I guess I'll do like one of those. So we have the area of a circle is 236 square inches. So 236 equals pi r squared, since we're looking for radius. So we're going to divide by pi to cancel that. And then we're going to take the square root to cancel that and get r equals the square root of 236 over pi. For the diameter versions, we would do the same thing, but I would personally start with the other formula where I'd say 857 equals pi d squared over 4. That way, once we've done the square root, we don't have to double it to go from radius to diameter. So again, we would divide by pi, we would multiply by 4, and then we would square root it, and that would give us our answer. So pretty simple problems. Then we have some sectors. Sectors are like the new thing, so we should probably do some practice on those. It says find the area of the sector formed by ACB, angle ACB. So angle ACB is 60. So we're able to do this one just like we did the practice up above in the notes. We know that this is 8 and 8, and it's an isosceles triangle. Oh, we don't need the triangle if we're not finding the segment, we're finding the sector. So now we're just doing 1/6 of the total area, which is pi times 8 times 8. I can simplify here and turn this into a 4 and a 3. So I have 32/3 pi square inches for number 8. And again, it would be a good practice to go ahead and type that in Desmos and see what it is as an approximation, but for time's sake, I'm just going to rush through a couple more of these to wrap up the video. Next one, we've got 1/3 of the circle. We have 120 over 360, so that's 1/3 of pi times 4.5 squared. So I would change that to a improper fraction and make it 9/2 squared. That way I can square that up and get 81 over 4. It might even be better to do 9/2 and 9/2. That way I can cancel out my 1/3 and make this a 3. So I get 27 over 4 times pi. And my units were square inches. So that's how we do those. This one's a little uglier. It's 110, and it's not a nice, evenly divisible thing. But when it's a degree measure ending in 0, you can just knock off these zeros, and your fraction is 11/36. So we have 11 over 36 times 12.8 squared. That's kind of terrible. I would just do that one in a calculator, honestly. We could simplify a little bit. So hold on, let's do 12.8. 12.8. So 36 is divisible by 4, and this is divisible by 4. So then we have, that's still really ugly. Yeah, I would just go to the calculator with that one. I could multiply it out by hand, but I'm really not in the mood right now. Here, just watch out with major arcs that they may be giving us a degree measure bigger than 180. So, like on this, we're doing the same stuff. Oh, they're giving you areas, okay. But still, we're relating that area to this angle measure, not to the 161. We're relating it to 199. Is that right? Yeah, to 199 degrees. So we would set up, so this is number 12, we would set up 199 out of 360 is going to be times pi r squared equals 84.14. So then we would be able to solve this for r. So we would do 84.14 times 360 over 199. And then we would also divide by pi, 199 pi, and then take the square root of the whole thing. So just basic algebra steps to isolate r. We're going to be multiplying and dividing and then square rooting. There's no adding or subtracting here because there's no pluses or minuses anywhere in the problem. So everything is solved by multiplication, division, and square root. This last section, I'll leave that one to you. It's the same kind of stuff. And then you have some practice with shaded areas. We've only did one of those, so let me go through one more of these and then I'll let you do the rest. So 22 looks kind of fun, so let's do that one. These are all nice little patterny things to where we have some kind of repeating pattern, I think. This one, we're going to think of this as basically moving these shaded regions together. So I'm going to think of my shading as being here and here instead of here and here. So that means I have the whole half at the top is unshaded, and then this center is unshaded. So I'm going to do this as 3 total shapes. We're going to think of our total circle. So the total circle is going to be A1, and our radius of our entire circle is 2 plus 3 plus 2. So it's going to be pi times 7 squared. So that would be if the entire shape was shaded. Then I'm going to take away the semicircle at the top. So I'm going to split it like this into a semicircle and take away the entire top half, because that'll all be unshaded once we move these 2 shaded regions down there. So A2 is going to be half of that. So basically, instead of doing A1, A2, I'll just think of my shaded region as a semicircle in the first place. And now all I need to take away, the only thing that's left in the shaded that I don't want, is this semicircle in the middle. So that's going to be the part I take away as A2. And that's going to be half of pi times 2 squared, because it's a semicircle with a radius of 2. And again, I'm going to do this as 2 times 2 so that those cancel. And we get 2 pi here. And up here we had 49 pi over 2. So we have 49 pi over 2 minus 2 pi. We can combine those because they're like terms. They're both in terms of pi. So to do that, we need this one to be halves as well. So we'll make it 4 pi over 2. And then our total area is A1 minus A2, which is 45 pi over 2. So the rest you should be able to do. It's just practice with these formulas and manipulating them. Hopefully not too hard.